Hey there, folks. It's been a while. I'll be honest, I'm a little nervous. I probably should have scripted this out. I've done this a few times this morning, trying to polish things up, but that's just not going to happen. So I just have to come out and say, hey, welcome to Calculus 1. This is a video series I'm putting together. Back when COVID hit, I was teaching Calc 2 and Calc 3. And to help my students, I put together a whole series of videos covering all of my lectures for those two classes. One thing though that's missing though, and I haven't taught a Calc 1 class since COVID, is a set of videos in the series for my Calculus 1 students. So that's what I'm going to do here, folks. My plan this semester and on this channel is to put up a whole series of videos covering my study of calculus, Calculus 1. And then my hope is to be able to go back and in coming semesters, Calc 2 and 3, in the coming semesters here, be able to kind of polish up and update my videos for those two classes also. Over COVID, I those were kind of put together in a mixed mash manner. I kind of jumped into it halfway through a semester and finished the back half of videos first, where the quality wasn't the greatest, and then came back at the beginning of the next semester and finished the front half of each video series, where things kind of did improve a little bit in quality, but my hope is to even polish things up a little further and give you an entire series overall, where it's a little bit more it'll fit nicer together, we might just say it that way. And to help me do that, one of the things I'm also doing this semester, I've been working on over the last summer, the last few months, and I'm going to continue to work on, is that I have a wealth of knowledge to share, and I have written that wealth of knowledge down by hand. I filled notebooks. I have written that wealth of knowledge down, have typed it up on the computer, and have filled up files and folders of that knowledge. But what I really want to do is get it out there and share that knowledge. So what I've been working on at the moment is really we might call it a book or a textbook, right, of calculus, my calculus, the way that I approach calculus. That's kind of where I'm at. I'm typing all this up from Calc 1 up through Calc 3 in sort of a textbook style, and going to try to make that available to my students in the end, and all students of calculus overall. Anybody that happens to stumble across my YouTube channel or find me out there, wherever I happen to place this book out when I do finally think about where it might be published. Certainly, I'm not looking at making a textbook like you might purchase for our class, but certainly give you and give my students and anybody at calculus a comprehensive and complete document that they can refer to, that is something that I've put together. So what you're going to see this semester as we go through the course is exactly that. What I'm going to give you access to, and here it is my my rough draft, right, of that set of notes here. And for Calculus 1, I'm about halfway through the semester with what I have written. And as we work through the semester, I'll be finishing up that second half, and along the way posting these videos covering the topics, right, from the semester. So what I like to do in my videos, if you've watched any of my Calc 2 or Calc 3 videos that I posted in the past, is I always like to write up something, right? And again, here, this is going to be kind of a comprehensive collection in the end, is my hope. Starting at Calc 1 and all the way through Calc 3 here, going back and trying to polish up the old stuff. But what I like to do is roll through my notes and roll through what's going to in the end be my textbook here. It has a lot of editing. It is a rough draft. Grammatically, it's going to need to be edited. That's for certain. Format-wise, it's going to have to be edited. That's for certain. And mathematically, it's going to have to be edited. And some of that mathematical editing will happen right here in my videos as I go through this with you. But what I want to be able to try to do for you is not only along with my textbook, but give you a kind of a lecture series that goes along with the book, so that you can rely on the two hand in hand. Sometimes it's, I understand there are students, and I'm one of those that really does have a difficult time just reading a math textbook and learning the material. Sometimes to get the ideas that are presented in the written word, it's sometimes nice to have a little explanation to go along with it. And that's what I'm going to try to provide with you here. And for students in my calculus courses, I always tell them that this is kind of an additional lecture. It's where it might be considered my formal lecture, where I'm going to present things to you very formally, defining things that you can see here as like definitions and theorems, and trying to give you as much proof as possible. Whereas in class is not so formal. If you've taken one of my calculus courses, I always say it's a little bit more of an organic process. My class periods, I always kind of gauge where students are at and where we're at in our learning, and each day really just depends upon those few things, where students' current understanding levels and where we kind of need to go. And I try to step out of some of the formalness to get us through that. So a lot of the formality you're going to see right here in this set of notes. And if you happen to miss class or anything like that, or if you want to go back and review anything that's been presented, certainly this is going to be a good resource. All right. Now, the study of calculus starts with this definition. When we think about calculus, calculus is the study of limits, right? I always say that the very first day in my courses. I always tell students, calculus, what we're studying this semester is calculus, and what that is a study of is what we call a limit in mathematics. And this semester in our study, that's where our study begins, is with beginning to try to understand what it means to be a limit. All right. Here we have in my notes, that's where I do begin the study. We do begin it here with the study of limits. And this first section of notes is really just going to try to be an introduction to limits. It is going to follow up with a little bit of application that my next video will take a look at, just to kind of give you a why. Why would we study limits? Why are these things important? And then follow that up with evaluating limits. How do we actually go about in a mathematical process and mathematical understanding begin to evaluate the value of a limit, all right, and get into that understanding. And then what we really wrap up with is kind of getting into some of the preciseness of what it means to be a limit. We're going to start the semester with a very informal definition of what it means to be a limit. But by the end of this chapter, this study on limits, the beginning of it here, this introduction to limits, this first quarter of the study of limits here for Calculus 1, we're going to look at some precise definitions for the limits, what's known as the epsilon delta definition. All right, so that is where we're heading. Calculus, again, is the study of limits, and that is what you study all the way out through Calc 3, as you study the concept of a limit applied in what you're going to see is 3 semesters worth of material. All right, a lot of different ways. It does start with basic understanding of limits and derivatives and integrals, but then takes those ideas and takes it all the way out into vector calculus, right, at the end of Calc 3. So it's a comprehensive study of this idea of a limit. All right. So we might begin with, that leads us to the idea, what is a limit? So what is a limit, right? Or really what I always like to say more specifically when we're talking about limits, what's the limit of a function, right? Limits are an operation that we apply to functions, right? And when applied to a function, what they're interested in is the limit of the functional behavior, right? So what is a limit, or more specifically, what is a limit of a function or a limit of a functional behavior, right, is what our study is in this semester, right? What does that mean? What does it mean to be the limit of a functional behavior? What does it mean to apply a limit to a function? Well, in general, right, what a limit describes is the behavior of the dependent variable in a functional relationship, right? In a functional relationship, you have a relationship between two variables. We can, in general, call them just variable x and variable y, but variable x and variable y are known more specifically as your independent and your dependent variables. Variable x being independent, variable y being dependent. Where in a functional relationship between variables x and y, in that manner, with that dependency, we often think of as variable y depends upon the value of x. X is independent. It can be whatever value it wants. Variable y depends upon the value of x in a functional relationship where y is dependent upon x, right? And x is independent. A limit, then, is interested in that dependent variable's behavior. It becomes interested in how does that dependent value, if we think about a function as having an input being the independent and the output being the dependent value, how does the output behave? And more specifically, how does that output behave as the input value behaves in a very specific way? Right? The input value is allowed to be independent. They can behave however it wants as long as it remains in its domain, right? As long as it remains a value that allows for a real number value as an output, right? It can be a value in the domain, right? It can be any one of those values. It can be independent. And as that variable, that independent value, that value of x changes, the value of y is also going to change, right? And a limit is interested in that behavior. The limit asks, as the independent value changes in this manner, right, as it changes in this very specified way, how does the dependent value change, right? It depends upon that independent value, most certainly, right, in that functional relationship. And as the independent value changes, it will change dependently. So as the independent value changes in a very specific way, a limit is interested in describing the dependent variable's behavior, right? That is what we think about with a limit. Now we can go a little further, right? We can take this into the algebraic realm and consider when we have the case where y equals some function of x, right? Here, consider having just some relationship between variables x and y where it's this functional relationship. Again, we know f is the name of the function, y depends upon x in this arrangement, right? X is independent variable, its behavior is independent, right? It can increase or decrease, we often think, with or without bounds. Right? It can behave in it can assume any value in its domain. And not only can it assume any value in its domain, it can change to any value in its domain. And as it changes, it's going to be increasing or decreasing. Right? We might be at the value of 0 in our domain and increase to the value of 10. Or we might be at the value of 0 in our domain and we might decrease, right, towards the value of negative infinity. Right? As we increase towards the value of 10, right, we are increasing towards a boundary, that value of 10. Whereas if we think about decreasing from 0 towards negative infinity, we're decreasing without bounds. And the independent values in a function where those values exist within our domain, right, can behave in that manner. Right? In this first case, I say, well, let's consider F's domain, right, where we can increase without bounds towards positive infinity. Right? We often note that mathematically or algebraically or in our study of calculus as x with this right arrow heading off to infinity. This is the notation for x approaching infinity, our independent variable approaching infinity. And we have an understanding that our value for x, right here down here in this graph, right, is beginning at some value less than infinity. Here I've just illustrated it at the value of 5, and is increasing, right, heading to the right along our number line towards larger values, towards the direction of positive infinity. Right? In a functional relationship, the limit is going to be interested in how the output variable behaves as the input variable behaves in that manner. Or possibly we could consider the case where x may be the independent variable increases towards the bounds of -1, right, from values less than 1. Well, that has its own unique notation. And in calculus, right, we indicate that independent variable behavior, right, as x approaching -1 from values less than 1. Now, it might be a little hard to see here, but there's a little superscript negative sign right there. All right? If you have the copy of notes, you should be able to see that. All right? Where what it's highlighting is that x is approaching the value of -1, but it's approaching value of -1 from values less than -1. Which, if we think about this as being the axis for x, it means that we're starting somewhere here, down here, below the value of x, x being equal to -1, below the value of -1 along the x-axis, to the left of it, and approaching it, heading towards it from values smaller than -1, less than it. All right? There are two ways we can approach this value of -1. We could approach, as we see here, from values less than it, and we can also approach from values greater than it. So we do want to be specific as to how that approach might be happening. And that's where we use this little superscript negative to say that we're coming from the negative direction towards -1. We don't need that superscript in the case here for infinity, right? As there's only one way to approach positive infinity, and that's from values smaller than infinity. Right? Both of these approaches are approaching values from less than, right? The negative direction, the smaller direction, from values less than the numbers of interest in our domain. Right? What's different here, though, is that this case is indicating an approach on an unbounded value, and this is indicating the approach on a bounded value. Right? The unbounded value of positive infinity, unbounded in the sense that you can never really reach that boundary. Right? Whereas in -1 being a bounded value is we could sit on the value of -1 and sit on that and say this is a boundary. We can't go beyond that location. And there's space, there's these values that exist beyond that location. In this case, that exists beyond it to the right, in the positive direction. Right? This is a little bit of notation that we see used in our limit notation. And what it indicates is the behavior for the independent value. What a limit is interested in is how does that dependent value behave? Right? How does that value f of x behave? Right? This value that's related to y, right? The output of the function. If we bring this up, let's see where I head with the notes here. Oh, well, one thing I first take note on here is, again, as I had noted, we can approach -1 right? From not only values less than it, we can also consider approaching it from values greater than it. And the way that we would indicate that in the notation, instead of using a superscript negative sign, what we'll see used is a superscript positive sign. Right? That superscript positive sign on the -1 here indicates that x is approaching the value of -1 from values greater than -1, which we can see is illustrated graphically here. We are at some value greater than -1. Now this location, right? This end of the what we might call the head of the arrow, the head of the ray, right, is that really just an arbitrary location, and its tail is moving in the direction of, right, the number, right here, -1, from values either greater than it or values less than it. Right? But where we start that motion from can be at any value greater than it in this case, right, or less than it in this case. These are really arbitrary locations. Right? So we also take note on that. When approaching a bounded value, right, like the value -1, right, there are two sides to that value, two sides to that boundary. You have a boundary that's to values smaller than it, right, where you can move to values smaller than it, and you have a boundary where you can move, well, a side of the boundary where you can move to values greater than it. Right? So we also have that notation used in limits. And again, this notation is used to indicate behavior of our independent variable. Right? So that's kind of where I begin with in the notes is limits are interested in the value of the behavior of the dependent variable as the independent variable behaves in a very specific way. So what we start with is indicating how do we denote the behavior of the independent variable. And that's what we see being used above. This independent variable x is behaving in this manner. And to illustrate it behaving in that manner, we use this notation in our limit. Right? Now here's an example of an actual limit statement. All right? Perhaps we have the case where as x heads to infinity, which we understand as being this behavior seen here, right? As our independent behavior behaves in this manner seen here, we're interested, well, what we see for the behavior of the dependent variable is that it decreases, and that it actually decreases towards, right, some bounded value at the value of 3, right? Some boundary of 3. At the bound of 3, right? The way we would state that using a limit, right? Using this thing that we're going to study this semester known as a limit would be this statement right here. Right? As we said, a limit is an operator that's applied to the function. Here's our function, f of x. Right? It's describing the relationship between our variables x and y that is in this functional relationship where y depends upon the value of x functionally. And again, what does that mean? That just means for each value of x, there corresponds just one value of y. For each input into the function, there's only one output. You can't have multiple outputs for a single input. That's dysfunctional. But for each input, if there's just one output, you have a functional relationship. Right? So for any functional relationship, you might have the case whereas x, the independent value, just grows without bound, just gets bigger and bigger and bigger, which is highlighted here in the notation as x heads to infinity. Right? This says the limit as x heads to infinity for our function f of x, right, is equal to the value of 3, meaning that the behavior that we see in our function f of x as the independent variable behaves in this way is that the value of f of x approaches the value of 3. And here, keep in mind, there are two ways that we can approach the value of 3. We could approach the value of 3 from values less than it, and we could approach from values greater than it. In a limit behavior, that approach of the value of 3, right, as x heads to infinity should only come from one direction, either greater than or less than it, right? So here we're going to decrease towards it, that boundary of 3. All right. Let's see here. So we would perhaps state our limit in this manner. Right? This is a statement for a limit. Right? This is the limit as x heads to infinity for function f of x being equal to the value of 3. That's how we read this item. Right? Now, I have a little illustration of what this might look like, right? To help us understand this behavior, right? To help us understand this limit statement above, right? This limit might be illustrated as follows, right? Where here we can see f is plotted, right? Here we have the graph of f, right? The graph is here in blue, right? What we do see is this dashed red line running horizontally at a height of y equal to 3, where the output of our function is equal to 3 right here, right? Where that horizontal dash line represents what we call a horizontal asymptote, right? It's this horizontal line, right, where the graph, right, its ends, specifically here its left and right ends, the end here on the left and the end down here on the right, right, approach that asymptote as x heads towards positive or negative infinity, right? And keep in mind, that's actually the behavior that we're interested in the value of this limit. This limit is asking, how does that function behavior, maybe we might say, how does that graph behave as the value we see along this horizontal axis, x, heads in this direction towards positive infinity as we move, starting at some arbitrary point smaller than infinity, and increase towards the value of positive infinity. How does the function behave? And because of this horizontal asymptote, what we see happen in the behavior is that it actually gets closer and closer and closer to the value of 3. Right? This graph illustrates this type of limit behavior. Right? It illustrates a limit, right, or the limit as x heads to infinity for function f of x being equal to 3. Right? Keep in mind again what a limit describes. It's describing this behavior, right? This behavior that we see happening in the output of our function, which is graphed along the horizontal, or sorry, along the vertical axis. Right? As my independent value heads to the value of positive infinity, what we see in this motion as x heads in this, well, as we move along our graph in this direction, is that for our outputs, for this dependent value tracked along this vertical axis, is that it starts to decrease. Right? As we said, we're going to see it decrease towards the value of 3. Right? It's not also going to be able to increase, because if we saw that increasing behavior, you wouldn't have a functional relationship. Right? So it's going to either have to increase towards 3 or decrease towards 3 in this behavior. And here what we see being illustrated is it decreasing towards the value of 3. As we think about moving along this graph in this direction as x heads to infinity, because x is independent, it's the value that's behaving initially, right? And y depends upon it. We see this output, this dependent value f of x, gets smaller and smaller and smaller, approaching the value of positive 3. It doesn't get smaller than 3 itself. And in fact, what a horizontal asymptote will indicate is that you actually never actually reach the value of 3 either. You get infinitesimally close to 3 in value, right, as you get infinitesimally closer and closer to the value of positive infinity for x. Right? Ooh, bring this up. A function that might give us this relationship would be this function seen right here. Right? This function f, described by f of x equals 3x plus 6 divided by x plus 1, is a function where if we take the limit, if we look at its independent value x, heading off towards positive infinity, what you'll see in the behavior for the dependent value, the value here for f of x, 3x plus 6 divided by x plus 1, is that that value will approach the value of 3. And we can see that here in the table. Right? I did arrange this table horizontally. The first row of the table, 0, 10, 100, 1,000, 10,000, those are the values of our independent variable. And what we see happening there is those values are approaching positive infinity. We might come back and say here, oh, those values are approaching positive infinity. Right? 0, 10, 100, 1,000, 10,000. Those numbers are getting larger and larger and larger. I could continue my pattern, but you'll see for the behavior of the dependent variable, right, we're starting to see already at 1,000 and 10,000 the behavior that we said we would expect or anticipate for the value of this limit. And we can note as x, that independent variable value gets larger and larger, approaches infinity, that this dependent value f of x, right, when it's 0, starts at 6, but then begins to approach the value of 3. Right? At 10,000, we're pretty close to 3 in terms of decimal value, right? To within precision of tenths, hundredths, thousandths, 10,000ths, right? Depending on where that next decimal place is. But what we end up seeing for the behavior here for f of x, right, is that we see f of x heads to the value of 3. Right? F of x is going to approach 3, right, as x approaches infinity. So the way that we say that with a limit statement is exactly what we said above. Right? And this is what we're trying to understand with this statement. This statement here is describing this behavior seen in the table here. As x gets larger, this dependent value f of x, right, this value seen in the second row, begins to approach this value of 3. Right? Starts at 6 when it's 0. At 10, it's 3.273. At 100, it's 3.030. At 1,000, it's 3.003. At 10,000, it's 3.000 if we round to 3 decimal places. It's getting really close to the value of 3. Right? What it's illustrating is exactly what we see here in the graph up above. As x heads towards, right, 100, 1,000, 10,000, this output value, this dependent value, is getting smaller and smaller and smaller, starting at 6 when it's 0, and getting really close to 3 in value when we're way out here to the right at 10,000. Right? That's the value of this limit. Right? I'll take a quick pause and I'll be right back, folks. Hey there, sorry folks, that little jump in time. Usually when I have to pause the video, I can do it pretty smoothly. Typically to pause, I'll just click over and make it show my notes only, and then I'll hit the pause button. And then some random time away, I come back without seeming like I've been gone too long, right? And you don't see the jumpiness of the pause. But yeah, every once in a while I'm making these videos, I do have to pause them. I don't want to do too much post-production. In fact, I do 0 post-production on my videos in most cases. I try to produce these videos all in one series here from start to finish just in one setting. Sometimes I do need to pause. Sometimes go fill up the coffee cup or answer the phone or just take a break if things are getting long. So, occasionally you'll see perhaps me disappear into the background, and usually that's a good indicator that I have to pause something. Or occasionally while reading through the notes or going through this text, I'll run across either errors or things that I could, that could be described better or more with more clarity. So I'll make changes. Maybe I'll make a pause there, or if I think I need to add something, I'll certainly pause there and make those changes and then jump back in. Yeah, I try to do a zero post-production. What I end up really doing here is I broadcast out using a piece of side software, OBS, and this is what I use to record these recordings and to stream on Zoom. This is what lets me layer in everything and lets me, use a green screen and all that good stuff. Is this program here, but you can see I can change around the upcoming scenes, and then I can set up this scene and then just hit the fade over button, and then that scene fades in. So yeah, I use a little bit of software help to make these videos so that I have very little post-production. But what I had forgotten to add was the one scene I used to make a pause, and that's this scene here, right? I could have just paused that for several minutes with that fade out and be able to come back and make it look right, not like it was paused. So it's a little behind the scenes here, folks. But yeah, I did have to take a quick break there. That video was getting kind of long, and it's still long, so let me continue here. I noticed I have a little bit more to add to this example. There is actually a way to visualize a limit, right? This particular limit, in this case, we see it's supported graphically, right? With this graph as our independent variable x heads off to infinity, as indicated here in the limit statement. Right? We would be traveling along the curve in this direction, heading off towards positive infinity, off to the right on our graph in the positive direction. And as we do that, we would be getting closer and closer to this horizontal line. This output, this dependent value, would be getting smaller and smaller and smaller, approaching the value of positive 3 in value. It's always going to be a little bigger than 3. And we can actually see that supported also in this table. All right? And that's where we get this result of 3 for the value of this limit. This is what we're saying with this limit statement. All right? A limit statement describes the behavior of this, the dependent value, as the independent value, that variable x that we see right here, as it behaves in this manner and heads off to, in this case, positive infinity. And what you see this value do is it approaches this value seen right here, the value of 3. And we see that graphically, and we see that right here in the table. And we can also illustrate that as we see here, right? We can separate out the two number lines, right? When we think about this behavior seen here, right, we're illustrating the graph of the functional behavior where we've taken both variable values and put them along a number line and then had those number lines intersect themselves at perpendicular to each other at a 90-degree angle to give us this graphical understanding, right, of this functional behavior. Right? We can separate out the number lines and think about these two values as being alone on the lines themselves. And when we make this statement here, right, the limit as x heads to infinity for 3x plus 6 over x plus 1 is equal to 3, what we are essentially saying is what's illustrated in these two graphs seen down here. Here we have the number line for x, and here we have the number line for y, which is our function of x, the dependent variable value. It depends upon x with function f as its relationship. Right? And as the independent value heads in this direction towards positive infinity, what we see happen for this dependent value is, right, it becomes smaller and smaller, right, approaching this value seen right here at the value of 3. Now, one thing we do note in our understanding is we don't really reach the value of 3, right? When we evaluate this function with this limit notation and say that it's equal to 3, doesn't necessarily imply that we obtain the value of 3 in our behavior, right? What it's interested in is how is that function behaving as x behaves in this manner. We might think, well, if we ever reached infinity, we would reach the value of 3 and we would eventually be able to fill in that dot, right? But because x can never reach the value of infinity, we technically can never reach the value of 3. And truly being a limit is, when we make this statement, is not interested in actually having to equal that value. It's interested in the behavior of the function. How is that behaving? Well, it's heading towards 3. Right? That's kind of what we're highlighting up here in the table. This value is heading towards the value of 3. Right? As the independent variable x, right, approaches the value of infinity, again, where we can see in this table. Right? That's how we understand this x is behaving. And that's being illustrated in these number lines as we see here. As x heads to infinity, the dependent variable heads towards the value of 3. Right? And it heads towards the value of 3 from values greater than 3. Right? We don't necessarily highlight that in our behavior here, right, or in the answer. Right? But we would expect that approach to come from only one direction in the case of x approaching positive infinity. It's not always going to be that way. Right? But we do note, starting here at x equal to 0, where are we starting at with a dependent value? Well, that would be starting at the value of 6. All right? This location seen right here as our dependent value. And as x behaves in this manner, starting at the value of 0, our dependent value starting at the value of 6 would approach the value of 3, but never actually reach it there. Remember, between any two locations on a number line, there's actually an infinite number of decimal values. So when we approach 3, we can approach it as 3.01, 3.001, 3.0001, or we could have a number of zeros between 3.0000 ... 1, right? We could have a number of zeros approaching infinity in there where, yeah, we can get infinitesimally close to the value of 3 and never actually truly be at the value of 3. All right? So that's what a limit is interested in. I do have another example. Let's quickly see if we can go through this one. Here I said, or perhaps we maybe have the case where as x approaches -1 from values, smaller than 1, or -1. X is going to approach -1 for values smaller than -1. We should understand what that means. That's, if we go back in the notes, that is this understanding here. We're going to think about x behaving in this manner. It's approaching -1 from values smaller than -1. Well, as that happens, back up. Right. We might think about the output of the function is going to decrease without bounds towards negative infinity. Right? And that can be stated in this manner. This is known as an infinite limit. And in fact, the limit beforehand was known as a limit at infinity. But here, this is known as an infinite limit. And what we might see happen is the dependent value f of x, right, as x behaves in this manner, right, the manner we've illustrated earlier in the notes, is actually going to approach negative infinity. Again, equal here is a bit of a, could be a little misleading. What we actually mean here when we say a statement involving a limit in this manner is that this dependent value is getting really, really, really close to this value here, negative infinity. Right? So close, it's fair to say it's equal to it. But as we all understand, in the case of negative infinity, you can never truly be equal to it. Right? So to help us understand a limit like this, we might see this kind of behavior. Right? Here's a function that illustrates this type of behavior. Here we can see the function in blue, right? Graphed out here in blue. This dashed vertical line is a vertical asymptote. And what do we know about vertical asymptotes from algebra? Those are locations in the domain where as x approaches those values, the output of the function, the dependent value, either goes up towards positive infinity, as we see over here on the right, as we approach that vertical asymptote, the graph goes up towards positive infinity, right, off the graph here. And as we approach from the left, it heads down towards negative infinity. That's what it means to be a vertical asymptote, where here we see a vertical asymptote actually at the value they tell us at -1. At this location, we're approaching in our limit. And how we're approaching is from the left. So we're coming in over here from the left. As we highlight, x is approaching -1 from the left. And on our graph, we would be heading down this graph, heading down, right? A dependent variable says towards negative infinity. Right? That's what we're saying with this limit statement above. That's the type of behavior we're describing. As x behaves in this way, the dependent variable is heading down, right? The y-axis towards negative infinity. Right? Because of that vertical asymptote at the value of -1. Right? What kind of function will do this? Well, here's a function that will behave in this way. It's just simply 1 over the quantity x plus 1. Right? This is a limit where as x approaches -1 from values smaller than it, 1 over x plus 1 will actually approach negative infinity. That's the graph of this functional relationship seen here. If we look at the table, right, we can see that behavior. Starting at -3 and heading towards -1 from values less than it, right? Here we are at -1.001. That's really close to -1, but slightly smaller than it, a little less than it, right? We see the output, the dependent value, go from -1/2 at -3 down to, well, down to, I guess, technically the value of -1,000, right? Approaching, right, smaller and smaller values that grow in their absolute value towards positive, will grow towards infinite values, negative infinity in a sense. At -1.001, we're at -1,000. We could imagine if we add a 0 here, right, that's going to add a 0 here. Right? So the closer we get to -1, adding more zeros, right, the closer the dependent value, right, is going to grow towards negative infinity. That's what a limit statement like this is saying. If we separate that out into separate number lines, what we see highlighted by this limit statement is this understanding seen here. Right? As our dependent value x, seen on this first number line, heads in this manner towards behaves in this manner, heads towards -1 from values less than it, right? Getting closer and closer and closer, right, with these smaller and smaller, well, closer and closer decimal values, right? What we see happen for the dependent value is what we see here. Right? It heads off towards the value, right, of negative infinity. Here we're at, what is this? -10 million, right? When we're at -1 and tenths, hundredths, thousandths, 10,000ths, 100,000ths, millionths, 10 millionths, right? When we're within 1/10 millionth of the value of -1, the output of our function is going to be at -10 million. Right? That is what we're describing in terms of this limit and its interpretation. Right? This is what we're studying this semester, is limits. All right? Again, we go back. Calculus is the study of limits. All right? What's a limit? Well, it describes the behavior of the dependent variable value, the value of the output, the value of y equal to f of x, right, as the independent value, the value that's allowed to just be what it wants to be independently, right, changes in a very specific manner. Right? As our independent value changes in a very specific manner in its independence, the dependent value is going to change very specifically dependent upon that independent value. And how we examine that is with the use of a limit, right? With the use of these limiting statements that we make here, right? Which essentially means this here graphically, or that we make here, right? Which means this graphically. Right? That's how we want to go about understanding this calculation known as a limit. Right? In general, let's kind of wrap up with this generic definition. Right? When we say something like, we have some function between x and y, and we want the limit as x approaches a for function f of x, and it equals the value of L, right? Means that as the independent variable x approaches the value of the value of a, the dependent value of y equal f of x approaches the value of L. Right? What this means is as our independent variable behaves in this manner, approaches the value of a, you might read that right arrow as approaching, this value f of x approaches, in the limit statement, the value of L. Right? As the independent variable behaves this way, as seen in the limit statement, the dependent variable behaves or heads towards this value of L. Now, one thing to point out, you'll notice in that generic form, as x approaches a, for the description of the independent variable's behavior, I did not use a superscript of plus or minus in sign, like we might see here or here, because what that statement actually implies is the directions from both sides. And in the study of limits, we can approach from the left in our study, we can approach from the right in our study, and we can also approach from both sides in our study, right? Which would be highlighted just as x approaches a. So in our most generic form, we consider an approach that approaches from both sides. All right. Now, the last thing we make note on here, and I'll finish with this, is that in the previous two examples of our limit statements, we supported those limit statements with both graphs and tables. And graphs and tables are going to be two of the fundamental ways you're going to go about interpreting the values of limits and go about beginning to understand the value of limits, right? This semester, you're going to have going into the course, and if not so refined throughout the course, a good understanding of functional behavior. All right? Given this function 1 over x plus 1, you do want to understand right away that graphically this is how that function behaves. Right? And that comes from decent functional analysis skills. All right? Now, before I crash everything here, I'm going to go ahead and stop for the day, folks. Switch this over and say that. But what I'm going to come back with in this video series is we're going to come back to an example of why we would want to study something like this behavior. And we're going to see a little bit more of this use of the notation little application, and then we're going to come back to actually looking at some other ways to begin evaluating these statements. I've given you the statements in their entirety to begin understanding them, but how are we going to approach these, right? When, for instance, all we know is the left-hand side. How are we going to figure out this right-hand side value? How do I know this is equal to negative infinity specifically? All right. We're going to get into that portion of the analysis. All right. So we're going to look a little bit at evaluating just a little further down the road. So bear with me there, folks. I've only begun to try to introduce limits to you, and we're going to come back to this a little bit more in the next lecture video. So I'll stop there and see you in the next one.